Okay, I again welcome you all, and today we'll be talking about the very foundation of modern quantum mechanics, what is known as Hilbert space. And to begin with the idea of the Hilbert space, it will be right if I start with an imaginal experiment. I would like to demonstrate an imaginal experiment in front of you so that you will have a feel of this mathematical space, because it's a space that accommodates mathematical functions. Now, if I imagine that I am a mathematician, okay? And I know the basic rules of mathematics. I know geometry. I can talk about a point in the space. I can talk about a line. I can talk about the plane. And I understand what a point is, what a line is, and what a plane is. And I would like to demonstrate the geometry around me with respect to a point, a line, or a plane. And I'm in an imaginal world. I'm a dreamer. I dream. And I'm walking, and I find there is a room. And there is a door in front of this room, and I can see some geometrical lines on the door. But the title that is written on the door is, I am an infinite room. I am a room of infinite possibilities. So I approach this door, and I open the door. When I open the door, I go inside the room. When I go inside the room, I see a different world. In my real world, I have X, Y, Z, as long as you talk about the Cartesian coordinates. But when I go in this world, I find there are infinite dimensions. And every dimension that I'm able to see in this room has a direction. There is symmetry. There is north, there is south, there is east, there is west. But there are certain directions which I cannot even imagine in my real life. I can see all of those possibilities in this room. And in this room, when I look at the points in this room, there are points that can represent the vectors. There are points that can represent the sound. There are points that can represent the waves. This room has infinite possibilities in it. And everything is happening in accordance with the set of rules. There is symmetry inside that room. And I find some of the points are very close to each other. And when I find that some of the points are close to each other, these are the states, these are the symmetrical states, these are equal states. I find some of the states are perpendicular to each other. And when these states are perpendicular to each other, we call them orthogonal states. That means the state 1 and state 2, suppose they are orthogonal to each other, these two states are completely independent of each other. So there are states that are completely independent of each other. There are states that are similar to each other. It's a very compact room. But at the same time, I can talk about the lines in that room. And between the lines, there exist the angles. So this room, with all possibilities, it's a mathematical room. I tell this room who you are, and the answer comes, I am the Hilbert space. So this demonstration that I try to demonstrate in front of you, this space is an abstract space. It comprises infinite possibilities. It accommodates infinite possibilities within it. And it can be made of vectors, it can be made of functions. There are numbers, all possibilities. And this space is called what? Hilbert space. But we as physicists use this space, but certainly we are not looking for infinite things always. We are interested in those things which have physical implications. So what we have to do here is we have to understand the basic mathematical formulation of this Hilbert space. Right? Any questions? Okay. So you have a space in front of you. You know about those vectors. You have vector, you have I, J, and K, right? You can have the dot product of these vectors, right? You know how to do the products, right? In the similar fashion, you have set of rules that makes this Hilbert space that you have to follow when you are working in Hilbert space. So to start with, the very first thing is, it is a linear vector space. So, there are vectors, and we have a space, what's called as linear vector space. And what does this linear vector space is made of? It's made of two things. One is called vectors, and another is called scalars. Right? So, your Hilbert space is made of a vector space. And in that vector space, you can represent that vector space as a combination of vectors and as a combination of scalars. So you have vectors and you have scalars. Now, if I talk about the vectors, you will not be, because when you go to the conventional domain of vectors, you rightly remember what a vector is. You have a line and then it has an arrow, right? And you call it a geometrical vector, which is giving you the magnitude as well as the direction. But here, your notation is not the conventional notation. You have an abstract notation here, okay? Because you are dealing with an abstract system. You are dealing with a space, what's known as Hilbert space. It accommodates infinite states in it. So you need a different kind of abstract generalization of these vectors. So for vectors, what do we represent? We can represent a vector by psi, we can represent it by zeta, we can represent it by phi, and so on and so forth. So here in Hilbert space, you have set of vectors. You represent the set of vectors as psi or zeta or phi or any other thing that is traditionally taken as a vector. Right? And you will have a set of scalars. A set of scalars. It can be A, it can be B, it can be C, it can be alpha, it can be beta, it can be gamma, and so on and so forth. Now, if I go back to my original bifurcation, I have vectors, these vectors, and the scalars. What they do, they make a linear vector space. They make a linear vector space, which is the part of your Hilbert space. Now, these scalars, they can be real numbers, right? And they can be complex numbers. Now, scalar here doesn't mean only real numbers. It can be the complex numbers. And when you say complex numbers, then automatically a thing comes into your mind is the complex conjugate of the complex numbers. Right? So when you have a complex number, you can take its complex conjugate by simply changing the sign of the number that comprises the iota. Right? So here you will have the scalars. These scalars can be real numbers, they can be complex numbers. Right? And vectors, they can be functions. And so this point is clear up to this now, right? Okay? So, any queries? If anybody wants to tell me anything, you can tell me. Now, since we are talking about the vector space, a linear vector space, it has to follow certain set of rules. Because in mathematics, what you do, you can come up with actions. You can have some actions and you can plan a mathematical manipulation and you can work on that mathematical model. In the similar sense, what we have here is we have a set of rules. Now the very first important thing is, now suppose in your Hilbert space, in your linear vector space, there are two vectors, right? One vector I call, say for the sake of argument, let me take it as zeta. Zeta is a vector, right? And there is another vector, phi. These are the two vectors. Now we have to extend this discussion to Dirac notation also, okay? But here I'm trying to take it on with the simplistic approach. Okay, so what is zeta? It's a vector. And what's phi? It's a vector. Now, if I take the linear combination of zeta and phi, what I'll get? I will get another vector, say psi. I'll get another vector. Now I have a vector, zeta. I have another vector, phi. There is a linear combination between zeta and phi, and you come up with a new vector, psi. This psi should also belong to the Hilbert space. It should belong to the Hilbert space in which you are enclosing the vector space, which is composed of the vector space. So, the linear combination of these two vectors will lead to another vector, And the vector that you obtain from it should also belong to your Hilbert space. So this is the first important condition that's linked with Hilbert space. Now another important property is the commutative property. Now all of you know the commutative property. So the vectors that you are dealing with, they must be commutative in nature. What does that mean? So if I choose my vector zeta and another vector phi, and the linear combination, the addition of these two vectors can be written in this reverse order. So if you add the two vectors and you reverse their order, the result of the two vectors is going to be same. So the vectors that are playing in this Hilbert space, the vectors that are existing in this Hilbert space, they have to follow the commutative law. They have to follow the commutative rule. Is this clear? Okay. So this is it. Now the next thing is associativity. Okay, associativity. So if I take my first vector as zeta and the second vector as phi and the third vector as psi, okay, you can write this as zeta plus phi plus psi, right? So this is associative property. So this is associative property. I have a bad handwriting, I can't help it. Okay, right? Fine? Now, suppose I have a vector, okay, and I add this vector to another vector. I have a vector, I add this vector to another vector, and I get the same vector back. What does that mean? Suppose zeta is my vector, I add this vector to say zeta naught, and what I obtain from this is only zeta. What I am obtaining? I am obtaining only zeta. I add this vector with zeta naught, and I get the original vector. What should be this zeta naught for you? Yeah?
Identity.
I can't listen what you were saying. Yeah.
Additive.
Additive.
Identity.
See, you have a vector, you are adding it to another vector, you are getting the same vector. There's no change on your vector. You are adding it, you're not multiplying it. So if you multiply it and you get the same vector, then you can talk about the identity vector. This is something that you know. Yeah?
Inverse.
Yeah, this is a null vector. So there should exist a null vector. So what does that mean? That means if I have a vector zeta, I add a null vector to it. This can be written as a null vector plus zeta, and this is going to give me back zeta. Right? Fine? Okay. So this is it. Now, for every vector that is existing in this space, there should also exist a symmetric vector with this vector. This symmetric vector is also called as inverse vector. Right? So that you have a vector, when you add this vector to its inverse, you have a vector, when you add this vector to its symmetric vector, you get a null vector. So there should exist inverse or symmetric vector. Now this is also called as symmetric vector. Right? So if I have zeta as my vector, I would like to add this zeta with minus zeta. So for zeta, there should exist a symmetric vector. There should exist an inverse vector. So that when you add the two, what you will get? You will get a null vector. Right? So these are some of the important properties of linear vector space. We are talking about the Hilbert space. Now let me go back to our conventional way of doing mathematics or doing the conventional physics. In conventional physics, what you have a vector, and this vector can have components. Suppose I have a vector R in two-dimensional plane, it will have two components. Yeah? You have a vector R, it will have two components. In terms of I, J and K. Okay? So if you have a vector, you can write it in terms of two components. Xi cap plus Yj cap. And if you have a vector in three dimensions, you will write this vector as Xi cap plus Yj cap plus. Okay? So what does that mean? So if I choose, say for example, I choose a vector A, and you can write down this vector as Ax I cap plus Ay j cap plus Az k cap. Alright? You can have another vector B as Bx I cap plus By j cap plus Bz k cap. Okay? These are your ordinary vectors, right? The vector A and vector B in three-dimensional space. Now, between these two vectors, you can have a product. Okay? You can have a dot product. Right? So, if you have a dot product, how you will calculate that? You'll call that vector A dot vector B. And you can calculate that immediately. That will come out to be Ax Bx plus Ay By plus Az Bz. Corresponding to this product, in Hilbert space, we have inner product. What we have? Now imagine, when you are talking about a Hilbert space, you are talking about the infinite dimensions. You cannot represent these infinite dimensions by arrows and the lines. You have to represent them using some abstract mathematical symbols, right? So, the product that you have between the two vectors in the Hilbert space is called as inner product. And the nature of this product can somehow be correlated with the dot product of these two vectors. Are you getting my point? Are you getting my point? So this is why I showed this example, so that I can connect with the inner product. Okay, so what should happen? You have this Hilbert space, the space that I talked about, that I gave you an imaginal world that we started this classroom with. And this Hilbert space carries vectors. It may carry functions. It may carry sound. Right? And between the vectors, there exists a product. And that product is called as inner product. That product is called as, so you have inner product. Now this inner product we can write in terms of cats and bras. When we will reach out to the Dirac notation, we'll talk about it. But here I will choose the two vectors. If I have to write the inner product of two vectors, how will I write it? I will write a bracket. I will write zeta. It doesn't look zeta. I will write zeta, comma, phi. Now the two terms that you see in this bracketed term, this implies an inner product between zeta and phi. Right? If you go back to A dot B, go back to that. Don't confuse yourself. If I go back to A dot B, A is real, B is real, I take the dot product, right? A dot B. I will get AX, BX plus AY, BY, AZ, BZ. And if I take B dot A, what you will get? You will get the same thing. But will it work to this abstract mathematical notation that we have? It will not work. Why? Because there is inculcation of complex numbers. And complex numbers, complex functions, they are not going to accept that kind of product. The inner product for real numbers will be valid. You can say for the real numbers, this zeta and phi is equal to phi and zeta. See, the order is important here. Here you are taking the inner product between zeta and phi, A dot B. And here you are taking the inner product between phi and zeta, B dot A. The two will be equal for real numbers. Are you getting my point? But you are going to encounter the complex functions. So this is not true. So what is true here? What's true here? If you have an inner product of zeta and phi, this is going to be equal to zeta and phi star. And you understand the star means the complex conjugate. But here, again, you have to follow a set of rule. What is that set of rule? The set of rule is that this star should be given to the first. So when you will come to the actual inner product, the star will come to zeta and phi will be kept as its. So zeta and phi is equal to zeta star and phi. Right? Now let us remodulate it a little bit. Now if I take on the same inner product, what we have zeta and we have phi. And I defined the phi as a combination of, say, alpha phi 1 plus beta phi 2. So now I have to write down the inner product. How can I write it? This is zeta, and then for phi I will be using alpha phi 1 plus beta phi 2. Now, what this distribution will be like? It will be, yeah?
Beta alpha phi 1 plus
It will be zeta.
Alpha phi 1.
So alpha I will write out. Alpha phi 1 plus
Zeta.
zeta
Beta.
beta zeta phi 2. Right? Okay? Now, if I replace the first by alpha zeta 1 plus beta zeta 2, this is a set of rule. Okay? So what's going to happen? So if I replace zeta by alpha zeta 1 plus beta zeta 2, what's going to happen? So now you have the inner product of alpha zeta 1 plus beta zeta 2 and comma phi. Okay, give me the same combination that you gave last time. What was that? Yeah, it was alpha
Zeta phi 1.
alpha phi zeta 1 plus
Beta 5.
beta phi zeta 2. But here you have to keep star. You have to keep the star with alpha and beta. So this is how you can modulate them. You can expand yourself to take on the various combinations between these vectors, so that you have more hand on the set of rules that's followed by Hilbert space. Now go back to that dot product. You have A dot B. Okay. Now if I want to calculate the magnitude of this A dot B, how I calculate that? Come on. I can think of A dot B is equal to magnitude of A, magnitude of B times cosine theta. So what will be AB equal to? That will be A dot B divided by cos theta. Or thinking other way, if I have a vector R, I want to calculate its magnitude, and I write down this vector in terms of Cartesian coordinates. What will be the magnitude of R? It will be under root of x square plus y square plus z square. Right? Now, calculating this length of your vector in Hilbert space is called as norm. It's called as norm. Right? And this norm, suppose I have zeta, I have to write the norm of zeta. It will be double mod. The double mod of zeta will give you what? Norm. And you know, when you take the dot product of the two vectors, what you get a scalar. And when you calculate the magnitude of these, when you calculate the magnitude of the inner product of these two vectors, it's always positive. Isn't it? So the norm of the vector that you're talking about in the Hilbert space, it has to be greater or equal to 0. Right? I think here